University of Kentucky chemistry professor John Anthony is making low-cost solar cells and transistors out of carbon instead of silicon.
Carbon is a lot more versatile than silicon. Silicon is basically a mineral. It's a rock, which means, you're very limited on how you can shape it. In order to get the silicon they use in a solar cell, you have to take sand and heat it with coal at thousands of degrees. Carbon-based materials can be processed. They can be molded and shaped at much lower temperatures. But right now, we're working on what's called a bulk heterojunction organic photovoltaic. It's a lot of big words strung together to describe a process that's ridiculously simple. You take a transparent conductor and you basically slather these organics on from a solution like an ink, and then the materials just spontaneously self-assemble into a working solar cell. One of the grants we just got funded for, we're trying to get a little bit more sophisticated and using inkjet printing techniques to make organic solar cells. So in this case, you'd put again, a transparent conductor sheet of plastic, which are easy to make, into an inkjet printer and use sort of our proprietary inks, and zit, 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 and out the other end pops a solar cell. What can we do on big scale? The dream I have is there are a lot of printing plants that are used to printing high-resolution, full-color images that are idle. So if we could just design inks to make solar cells that way, think of the speed at which you could just start printing off solar cells. Lightweight, flexible, you can put them on everything. You can coat the windows of skyscrapers with solar cells and start generating some of the energy that's used to cool down the skyscraper. So there's a lot of potential if we could just get the scale up.
Outrider Technologies, a company formed in 2005 based on Anthony's research, is making organic transistors for flexible flat panel displays.
We've been able to put transistors, basically circuits, integrated circuits, on saran wrap. So plastic that's thinner than this, we can actually build circuits on, and we can wrinkle it up and crumple it, and it still works. We just submitted this for publication to one of the Nature journals. So we know we can do this basic circuitry and that it's stable, it doesn't die when you crumple it up and fold it and stuff it in your pocket, right? The next question is, can we get the performance out of it? And that is where a good-sized effort of my research group is now turning its attention.
With grants from the Navy, NSF, and industrial sponsors, Anthony's research team recently moved into the new laboratory building at the UK Center for Applied Energy Research.
So now that I'm out here, I basically have doubled the number of current active research grants, just because I now have the space to support people. What we have to do as chemists, we have to figure out what needs to be made. We have to then figure out how to make it, and then we got to do the initial screening to see if it's going to have the right properties. My graduate students in my group, right, they need to know an awful lot of physics, they need to know a lot of electrical engineering, they need to know a lot of materials engineering in order just to figure out what molecule needs to be made, and then all of their chemical knowledge can come into play. There are a few things in the world better than having a different point of view. I really like having ideas thrown at me from every single direction and using those ideas to feed into new projects. I can't tell you how many new projects and how many grant dollars have been brought up because I've gone to a seminar that's completely out of my area and hearing somebody complain saying, we could really advance this field if we could only do this. I know how to do that. And then a collaboration is born.